For the next couple of days, we will be reviewing polynomials and their end behavior. Now, a polynomial function is normally a function that can be written as a series or sum of powers, such as a polynomial function could be something like 3x squared minus 4x cubed plus 7. Now, a lot of times what we do with polynomials is we can factor them. So I might have an example like x minus 3 squared times x plus or minus 1 cubed plus x to the fourth, and more. So we have two different ways we can look at factors: their normal form or their factored form. Both can be sketched and drawn using a simple set of steps, which we're going to be talking about over the next few days. But first, let's review end behavior of a polynomial. Now, the end behavior of a polynomial is simply stated what happens as the x value goes to infinity. We often call that the left or right hand behavior. Now, we're going to go into that more later on, and especially that becomes important in calculus for us. But first, let's talk about how we find end behavior of a polynomial. To do that, we need to identify its type. Now, a standard polynomial is always written in the form y equals ax to the n plus bx to the n minus 1 plus cx to the n minus 2, so on and so forth, where n is the power and it just gets smaller as we go on. A is the coefficient. Now, we classify polynomials in 4 different categories. We call them their types. This is also sometimes called the lead coefficient test. Now, if the power is even, in other words, if n is even and a is positive and the coefficient is positive, we have what's called an even power. Now, an example would be something like y equals, let's say, 3x to the fourth, or just x to the square, or something along those lines, where the number is positive and the power is even. All these basically have the same shape. They look like a parabola. Now, if the power is even and the coefficient is negative, then what happens is we flip it. We get a vertical reflection. This might be something like negative 3x to the fourth or negative x squared, and so on and so forth. These look like an n, an upside down parabola. Now, if we go to an odd power, so if n is odd, and a nice example here, y equals x cubed, y equals 4x to the fifth, and so on and so forth, we get our cubic looking graphs. And if the power is odd and negative, what happens, again, we get a vertical reflection, like negative x cubed, negative 4x to the fifth. We get opening just like a cubic, but going backwards. Now, what happens here, we sometimes call these end behaviors, what's happening at the ends, because the little arrows are what we call the ends, the end. And that's what we call end behavior. So the one on the left is what we call the left hand behavior. The one on the right, of course, the right hand behavior. And in calculus, we call it left hand limit, right hand limit. What's happening as we go on to the left and what happens as we go to the right. Now, if you notice, if it's an even power and positive, they both go up. If it's even and negative, they both go down. Odds, it depends on the sign. One side goes down while the other side goes up, and it flips for the odd negatives. And that's what we're going to talk about real quickly next. Okay, what we call end behavior. So, end behavior of a polynomial, remember, if it's simply stated, if it's even positive, it looks just like you. You just look even and positive. It's happy, so it has a happy face. On the left hand, it goes up to infinity. On the right side, it also goes up to infinity. Now, if it was even negative, it got flipped. It goes down to negative infinity. And the same thing on the right side as well, down to negative infinity. Looking at an odd positive, this goes, on the left side, it goes down to negative infinity, but on the right side it goes up to positive infinity. That's pickup line number. Hey, what's your sign? I'm even positive. I'm always happy. All right, odd negative, we flip it. This on the left side it goes up to infinity, and on the right side it goes down to negative infinity. So these help us determine what the graph looks like. So a lot of times we can tell what's happening on a function without actually looking at the graph itself. For example, let's take a look at the example y equals 3x to the fourth minus 5x cubed plus 7x minus 1. I can know what this graph basically looks like in the end. Now, in the middle part I don't know, but I know because my lead coefficient here is even and positive. This graph, we call it even positive, this graph will therefore look like a parabola in the end. Whereas if I have something like y equals negative 1/3 x to the 7th minus 4x cubed plus 2, my lead coefficient here is odd negative. Now, I don't know exactly what the graph looks like, but I know if I go off into the future, it's going to look like this in the end. And you can take a look. Graph this on your calculator. Zoom out quite a bit. Let your x go from negative 100 to positive 100. Adjust your y's accordingly, and you'll get this graph here in the end. Now, the question that most people have is, what do the powers, like the fourth power, the seventh power, have to do with the graph? This looks like a parabola, but what does that 4 do to it? It's not necessarily a parabola, but what does that 4 do to it? The 7 tells me it looks like a cubic, but it's not exactly a cubic. What does that 7 do to the graph? And that's what we're going to talk about next. Find the root for f of x equals x minus 3. And what is the difference in these graphs? Well, the root is easy. The root, remember, this is where the graph equals 0. So if I solve it, my root is 3. Well, if I graph the first one, we all should know this one. This is just a line. At 3, it crosses through the line. Okay? Now, the next one, it has the same root, x equals 3. They all have the same root. But when I graph it this time, the 2 tells me it's a parabola. This tells me it's even positive. So it's going to look like a parabola. So when I go to the 3, it's going to look like a parabola at 3 and go through it. It bounces off. This is called M2. And what M2 means is at the root, it makes a parabola. It makes a parabola at our root. Now the 3, it's also the same root, x equals 3. So at x equals 3 on my graph, what does the 3 do? It tells me it's odd positive. So it has to look like a cubic graph. This is our cubic graph. Odd positive, so what's it going to do? It starts down and ends up. Now those are pretty simple to do. We call this M3. So at the root, it makes a cubic graph. So what do the 4s and 5s do then? We've never graphed a quartic or a quintic group. Very simple. All I have to look at the power, it's even, and my sign is positive. So it will look like a parabola at the 3. But what the 4 does is it widens it. The 4 makes it wider, okay? So it's going to make, instead of like a normal parabola like we did here at 3, whoop, that shouldn't be a 4, that should be a 3 there. What's going to happen here at the 3, it gets wider at the base. So basically, all even roots look like a parabola. They only get wider depending on the power. And that's the same thing for fifth roots. My root here is still x equals 3. It's still odd, and positive. It's still odd positive. So it's going to look like our cubic graph. The only difference is at 3, it just gets wider. So all odd roots look like a parabola. Now, I have a supplement here. I would encourage you to watch it, and it'll help you how to remember these. Now, when you go to part 2, we're going to take a look at graphing some of these, so make sure you go to part 2.